Welcome to Deep Space Drift. Tonight's journey follows the quiet life of a sun-like star, from steady fusion to a swollen red giant, from a fading planetary nebula to the calm glow of a white dwarf remnant. If this kind of slow science storytelling helps the mind unwind, tap like and subscribe for more long-form space documentaries. Settle in, let the light soften, and let the universe drift by one gentle chapter at a time. How can a star appear steady while its interior never rests? A sun-like star lasts because inward gravity and outward pressure match at every depth. At the visible edge, light leaves a thin, bright layer. From far away, the disk seems smooth. Closer in the surface breaks into a slow mosaic of bright cells. Narrow, darker lanes thread between them like river channels. The darker lanes mark cooler gas sinking. The brighter cells mark warmer gas rising. The pattern drifts and reforms without hurry. Brightness is not a hard shell of fire. It is a boundary where trapped energy finally slips free. Just beneath that boundary, pressure changes with depth in a smooth gradient. Each lower layer carries the weight of all the layers above. The weight squeezes the gas tighter. The tighter gas pushes back. This support is spread through the whole volume. Gravity pulls inward on every particle. Heat keeps particles moving in every direction. Their motion creates pressure that resists the pull. When the pull wins by a small amount, the gas contracts and warms. When pressure wins by a small amount, the gas expands and cools. These tiny adjustments cancel each other again and again. That is why the surface can look calm for ages. A descent from the surface toward the center crosses layers that grow denser and hotter. The glow deepens from pale gold to a bright white glare. Deeper still, the light is no longer a surface glare. It is a dense radiance spread through thick gas. No hard wall appears between regions. Temperature rises step by step. Density rises step by step. One layer blends into the next like color blending in a sunset. Even the idea of a single inside and outside becomes misleading. The star is a continuous body with properties that change smoothly with depth. In that region, matter behaves as hot gas with charged particles mixed throughout. Collisions become frequent enough to blur any simple path. Motion is present everywhere, yet it rarely becomes turbulent at large scale. The interior holds itself with gradients rather than edges. Near the center, the squeeze becomes extreme. The core reaches about 15 million degrees. That is far hotter than the hottest air in a thunderstorm. At this heat, collisions become so energetic that atomic nuclei can come close enough to join. Fusion is when light nuclei join and release energy. In a sun-like star, hydrogen joins into helium deep in the core. The release begins as a tiny change in mass. It becomes a large store of energy spread through countless reactions. The energy first appears as faster motion of particles. It becomes heat. It becomes light. A simple rule emerges from this center. If fusion slows, pressure drops, and gravity tightens the squeeze. If fusion speeds up, pressure rises, and the core eases outward. This self-balancing feedback keeps the core from running away. The star shines because it continually corrects itself. The energy made at the center does not stream straight to space. Light behaves as a mote of dust in very dense fog. It moves a short distance and scatters. It turns and scatters again. Any original direction is lost almost immediately. The path becomes a slow random drift outward. Each scatter shares energy with the surrounding gas. Each scatter delays escape. Over immense time, this repeated scattering turns a fierce central release into a gentle outward flow. A bright point at the center becomes a broad warmth across many layers. That is why the surface does not flare with every change in the core. The interior acts like a deep haze, and the haze is made of the star itself. A slow visual scene forms inside this haze. Countless flashes of light appear and vanish in place. They are not separate sparks. They are brief transfers of energy from particle to particle. The transfers spread outward like ripples that never make a clean ring. They fade and reappear as the gas jostles, Farther out, density drops and heat finds more than one route. In some layers, scattering light carries energy outward step by step. In other layers, warm gas rises while cooler gas sinks. Rising flow carries heat upward in broad rolling cells. Sinking flow returns cooler material downward. The boundary between rising and sinking shifts constantly. It forms a moving web of currents rather than a flat sheet. At the surface, these currents break into the bright mosaic again. Dark lanes form where cooler streams descend. Bright cells form where warmer streams reach the top. A small understanding locks into place. The surface pattern is not decoration. It is the visible trace of deep transport at work. Yet another limit sits quietly inside all this description. The interior cannot be seen directly. No escaping light carries a clear picture of the core. Scattering erases detail long before light reaches the surface. Many different depths contribute to the final glow and their signals overlap. The surface shows only the last stage of the energy journey. It cannot provide a sharp map of what happens at the center. Fine structures deep inside remain inferred rather than observed. Only broad effects can be trusted with confidence. For example, the overall brightness and the gentle surface motions reflect averaged conditions. Small variations at depth blur into the background. This limit matters because the star evolves slowly. The changes are real even when they cannot be watched directly. The balance that holds a sun-like star is therefore both robust and delicate. It is robust because pressure adjusts quickly when gravity changes. It is delicate because the fuel at the center slowly changes composition. As hydrogen becomes helium, the core conditions shift. The star responds by rearranging its layers over very long time. Steady shining gives way to distinct stages, each guided by the same simple forces. Gravity continues to pull inward. Pressure continues to push outward. Energy continues to leak away as light. Nothing in this balance requires drama. It requires only patience and physics. Before any long-lived stability can exist, the star must first assemble from colder material. In the next view, a dark cloud contracts and thickens. A newborn center warms until fusion can begin and the long balance is set. How does a dark cloud decide where a star will appear? A sun-like star begins when gravity tightens a cold pocket of gas faster than heat can escape. In that region, the cloud looks still. It is not smooth. Thin dust makes the space dim and brown. Light that enters is scattered and absorbed. Brightness fades into a soft gradient. Within the gradient, long filaments run like quiet rivers of shadow. Along each filament, denser beads form at irregular spacing. Each bead has a colder center and a warmer outer skin. The boundary is not sharp. It is a gradual thickening layer by layer. Darkness is not emptiness here. Darkness marks where matter is thick enough to hide what lies behind it. At this distance, the filaments resemble folded dunes of shadow laid in slow waves. Faint knots sit where the folds cross. Some knots grow heavier than their surroundings. Gravity strengthens there. Pressure tries to push back. Pressure is the random motion of particles resisting compression. As the knot cools by radiating energy away, that resistance weakens. The inward drift begins. It starts as a gentle slide. Gas follows the deepest part of the density gradient. Dust rides along with it. The knot contracts and warms. The warming is subtle at first. At the edge of the knot, heat escapes more easily than at the center. The outer skin cools and becomes denser. It slides inward and thickens the core. A faint temperature gradient forms from warm outside to hotter inside. The gradient is smooth. It is measured in layers rather than steps. A dust grain is smaller than a drifting ash flake, yet countless grains together can dim a whole filament. This gentle scale shift matters. Small particles control how quickly energy leaves. That speed controls how quickly gravity can take over. Cooling is the quiet door that lets collapse proceed. Heat spreads outward through collisions, yet the center continues to densify. The process resembles a snowdrift building under a steady wind. Most snow settles slowly. A slight hollow traps more flakes than nearby ground. The hollow deepens without sudden motion. Each added layer makes the next layer easier to keep. Collapse does not need a shove from outside. A small imbalance is enough when it persists for a long time. As material falls inward, it rarely falls straight. The cloud has tiny twists from turbulence. Those twists become rotation as the knot shrinks. Rotation speeds up because the turning radius becomes smaller. Spinning gas cannot all reach the center at once. It spreads into a flat disk around the densest point. The disk is thin compared with its width. It has a bright inner rim and a cooler outer band. The midplane is the thickest layer. It casts a narrow shadow through the surrounding haze. A faint glow sits at the center. A dark ribbon slices across that glow where the disk blocks light. Above and below the haze is lighter and more transparent. In that region, motion organizes itself into streams. Some streams curve into the disk. Some streams skim past and return on wide arcs. Gas in the disk rubs against nearby gas through endless small collisions. Those collisions spread heat. They also shuffle angular momentum through the disk. The disk is not a decorative ring. It is the pathway that lets matter move inward while some spin is carried outward. Without that exchange, rotation would stall the collapse far from the center. The central object is still not a true star. Protostar is a forming star hot but not yet fusing hydrogen. It shines because compression turns gravitational energy into heat. That heat leaks out slowly. It warms the nearby disk surface. It warms the inner envelope around the disk. Why it matters becomes simple. This heat sets the starting conditions for the long stable phase that follows. Time stretches across a quiet scale shift. The main growth of the protostar takes about 1 million years. That span is like 1 million gentle tides reshaping the same coastline. Within that long span, the disk changes much faster. Clumps form and shear apart. Spiral patterns appear as slight overdensities. Each spiral is a shallow ridge in the disk surface. It guides gas inward in slow steps. A warm arc forms wherein falling material meets the disk. The arc is not a hard shock wall. It is a broad band where density and temperature rise together. At this distance, the band looks like a dim crescent embedded in dust. Early light comes from falling and squeezing, not from nuclear fire. As the protostar grows, pressure rises in the core. The core becomes more uniform. The outer envelope begins to loosen. Heat puffs the gas outward. Gravity continues to pull inward at the same time. The result is a layered compromise. Some gas keeps feeding the disk. Some gas drifts away into the larger cloud. Two faint cavities open above and below the disk plane. The cavity walls are brighter than the surrounding dust. They scatter the central glow outward. The shape resembles a soft hourglass. The disk mid-plane remains the darkest stripe. Here, a limit of observation becomes unavoidable. Dust hides the mid-plane and the inner disk. Visible light cannot trace the detailed flow near the center. Even longer wavelength glow blurs as it passes through thick layers. A signal would reveal only average structure. Fine streams and small clumps remain inferred from their effects. Mass growth can be estimated in broad terms. The precise path of any single parcel cannot be followed. That limit shapes what can be known about the earlier stage. Yet the larger trend is steady. More mass settles into the center. The disk gradually loses material. The surrounding cloud becomes thinner and less opaque. The dark ribbon across the glow grows narrower as the disk evolves. The protostar approaches a threshold where compression alone is not enough. In the next passage, the core becomes hot enough for sustained hydrogen fusion. The long outward journey of energy begins in earnest. What begins the long, calm shine inside a sun-like star-sustained hydrogen fusion in the core provides a steady outward flow of energy. Deep inside, pressure rises with depth in a smooth gradient. Gas grows denser and hotter without any sharp boundary. The core is not a rigid ball. It is a region where temperature and density reach their highest values. Inser and deeper collisions become more frequent. In that crowded space, hydrogen nuclei move fast enough to come close together. Fusion is when light nuclei join and release energy. The joining does not happen everywhere. It favours the deepest central volume where the squeeze is strongest. A quiet threshold is crossed. Compression no longer provides most of the power. Fusion takes over as the main source of heat. The star stops being a warming object in formation. It becomes a stable engine. At this distance, an interior cross-section looks like a pale pearl, wrapped in many translucent shells. The shells are not walls. They are layers where conditions change smoothly. Near the centre, energy appears as heat and as high-energy light. That light does not travel outward in a straight line. Light behaves as a drifting seed in thick mist. It moves a short step. It scatters off charged particles. It changes direction. It repeats this countless times. Each scatter shares energy with the surrounding gas. Each scatter blurs any memory of where the light began. The result is a slow outward leak, rather than a beam. A small payoff settles in early. The core can release energy quickly. The surface can stay calm because the interior delays the escape. This delay acts like a deep buffer. A bright inner source becomes a gentle outer glow. The star can shine steadily, even while the core remains intensely active. The buffer is not an added layer. It is made of the same gas. Density is the key. The denser the layer, the more often light scatters. The more often it scatters, the longer escape takes. A single packet of energy can spend about 100,000 years wandering outward. That span is like a glacier slowly reshaping a valley wall grain by grain. The number is large, yet it follows from tiny steps. Each step can be shorter than a grain of sand. The journey becomes long because the direction is constantly scrambled. This is a gentle scale shift from the smallest collisions to a time scale that dwarfs storms and seasons. Another quiet payoff appears. The long delay smooths short changes in the core. A brief increase in fusion does not immediately brighten the surface. The extra energy first warms nearby layers. Those layers expand slightly. Expansion cools the core region. Cooling reduces fusion. The cycle pushes the core back toward balance. If fusion slows, the opposite happens. The core contracts. Compression warms it. Warming increases fusion. This feedback keeps conditions steady for immense time. It behaves like a thermostat made from gravity and pressure. No external hand is needed. The star regulates itself because the laws link temperature to pressure. Pressure links to density. Density links to how gravity squeezes. In that region, the regulation is continuous. It never finishes. It works by tiny corrections. Each correction is small enough to feel like stillness when viewed from far away. The interior remains layered. Above the core, a broad zone carries energy outward, mainly by scattering light. The gas there is stable against large overturning motion. It is not motionless. Particles still collide. Energy still drifts outward. The drift is slow and steady. A second interior scene forms. Faint zigzag traces appear through the radiative layers. Each trace is a short hop of light before the next scatter. The traces do not form straight rays. They form a tangled weave. Brightness is higher at deeper layers. It fades outward as energy spreads through a growing volume. The fade is smooth. It resembles a dimmer turned slowly rather than a lamp switched off. Another small payoff locks in. The star does not store its light in a cavity. It stores energy as heat distributed through gas. That heat is the true reservoir. Light is only one form the reservoir takes on its way outward. The outer layers respond to the reservoir. When the reservoir grows, the star expands a little. When it shrinks, the star contracts a little. These shifts are gentle. They keep the balance between gravity and pressure. A limit of intuition appears here. The core cannot be pictured as a clean sphere with a clear edge. The transition from core to surrounding layers is gradual. No direct image can confirm the detailed pattern of fusion in the center. Scattering erases detail long before energy reaches the surface. A signal would carry only blended information. It would reveal averages rather than fine structure. Even the deepest temperature profile is inferred from surface effects. Those effects are subtle. They can match more than one internal arrangement. The limit is not a failure of physics. It is a limit of what escaping light can preserve. The core remains real and active, yet its details stay hidden behind layers that act like a blur. This soft uncertainty encourages cautious language about the innermost region. Another quiet payoff follows from that blur. The surface brightness is a delayed report of old conditions. The light leaving the star now can reflect core changes from long ago. The star therefore contains a kind of time lag within its own structure. The lag is not a memory like a record. It is a travel time created by countless scatters. It turns the star into a slow system. Many changes take place inside before any change becomes visible outside. This lag also means that stability can persist. The star is not easily pushed into rapid swings. Energy must first work through deep layers. The outer boundary remains smooth in its average glow, yet fine texture still appears on the surface due to convection closer to the edge. The texture is the last stage of transport. It is shaped by rising warm gas and sinking cool gas. That motion becomes more important in the outer layers where density is lower. The story now moves outward from the radiative interior toward that churning skin. The next passage follows how energy chooses its final path to the surface. It shifts from scattered light to slow, overturning flow still calm and steady. Why does the outer skin of a sun-like star look restless while the whole star stays steady? The outer layers move because convection becomes the simplest way to carry heat toward the surface. Near the top, light escapes from a thin boundary called the photosphere. Photosphere is the thin layer where visible light escapes. It is only about 500 kilometers thick, like the width of a vast desert basin. This thinness creates a surprisingly crisp edge to the star's disk. Light comes from a narrow range of depths where opacity changes quickly. Below that range, scattering grows so frequent that the glow is trapped again. Beneath this thin layer, gas remains dense enough to delay light for long periods. Opacity is how strongly matter blocks light from passing through. When opacity is high, light struggles to slip outward by scattering alone. Like smoke thickening in a narrow canyon, each step of light becomes short and wandering. Heat then finds a faster route by moving the gas itself. Convection is heat carried by rising warm gas and sinking cool gas. Warm gas expands slightly, so it becomes lighter than its surroundings. It rises in broad columns that slow near the surface. Cooler gas collects and sinks in thinner sheets between the rising columns. At this distance, the upper convection zone resembles a field of dark and bright islands. Bright patches mark where hot material reaches the photosphere. Dark lanes mark where cooler material slips back down. The boundaries are narrow, and they curve like braided channels. The pattern is never fixed, yet it remains statistically similar over time. A small understanding settles in early. The mottled surface is a direct trace of heat transport, not a separate decoration. Energy created deep inside is turned into motion near the edge. Motion then turns back into light at the last thin layer. Another slow scene forms at the star's rim. Brightness fades toward the edge in a smooth gradient called limb darkening. The rim looks dimmer because sight lines there pass through cooler, higher layers. Near the center of the disk, deeper and hotter layers are visible. Near the limb, the view skims along shallow layers that radiate less intensely. This is not a shadow cast by an object. It is a geometric effect created by layered temperature. The same idea explains why granules appear sharper near the center and softer near the edge. At the limb, bright cells blend together through the slanted path. Fine lanes lose contrast as light crosses more material. Another understanding unlocks quietly. The surface is not an even curtain. It is a translucent skin whose depth changes with viewing angle. At a microscopic scale, photons scatter from free electrons and ions. At a larger scale, whole parcels of gas rise and fall. Both processes occur at once, and they trade dominance with depth. Deeper down, scattering light can still carry a large part of the heat flow. Higher up, convection takes over where opacity makes radiation inefficient. Between these regimes, a transition layer appears. Rising plumes overshoot into slightly more stable gas and then slow. They spread sideways like a low cloud, flattening beneath a cooler layer. That sideways spread feeds the darker return flows. The return flows gather into narrow downdrafts. These downdrafts are cooler and denser, so they sink more readily. The downdrafts can reach far deeper than the bright upflows. This asymmetry matters because it mixes material through a thick region. Mixing keeps the outer layers chemically uniform for long spans. It also helps carry heat without needing light to do all the work. A second visual anchor emerges in the interior. Long pale plumes rise through a background that darkens with depth. Between them, thin descending curtains form. The curtains sharpen as they fall and they pull surrounding gas inward. Gradients of temperature and density remain smooth even in motion. Nothing resembles a rigid pipe or a hard boundary. Everything is a continuous flow shaped by buoyancy and pressure. A gentle scale shift becomes clear. A single rising plume is tiny compared with the star. Yet the combined pattern covers the whole surface at once. Local motion creates global steadiness because many cells average together. Short-lived features can flicker and vanish while the overall brightness stays calm. That calm does not mean the motions are weak. It means the motions are balanced in aggregate. Heat carried upward is matched by heat radiated away. Another small payoff settles into place. Convection acts as a self-adjusting circulation near the surface. If the surface cools slightly, the temperature contrast increases. Rising flow becomes more vigorous, and more heat reaches the photosphere. If the surface warms slightly, the contrast decreases and the flow softens. This feedback damps rapid swings in surface temperature. Yet convection also has limits. It cannot carry unlimited heat without changing the structure of the outer layers. When energy flow changes, the depth of the convective region can shift. That shift alters which layers are mixed and which layers remain stratified. Here the limit of observation becomes important. The deeper convective motions cannot be seen directly. Only the surface pattern and the limb gradient are visible in escaped light. Everything below the photosphere is inferred from its effects. The flow spans many swirling scales at once, from broad plumes to tiny eddies. Escaping light blends these motions into an average pattern. Small structures remain below the resolving power of any signal that escapes. This is a limit of resolution set by scattering and depth mixing. It means details of mixing and overshoot remain uncertain in fine grain. Even so, the broad picture is secure. High opacity favors convection near the surface of a sun-like star. Convection imprints a cellular texture on the photosphere. Limb darkening reveals that temperature changes with height. These three facts fit together without strain. They explain why the star can look textured yet radiate smoothly. They also prepare the next step inward. Below the moving skin, pressure rises with depth in a long, steady gradient. In the next passage, that gradient connects outward heat with inward gravity. How can a star keep a steady shape without any solid frame? A sun-like star stays stable because gravity is matched by pressure at every depth. At this distance, the bright disk seems simple. Its edge is crisp. Just under that edge, light escapes from a thin, luminous layer. Below it, the star is continuous gas. Density rises inward. Temperature rises inward. Pressure rises inward as well. The rise follows a smooth gradient rather than a step. Each deeper layer carries more weight from above. That weight is not carried by a rigid shell. It is shared by the gas itself through pressure. A slow interior view shows no walls. It shows only layers that shade from lighter to darker, then back to brighter toward the center. Hydrostatic equilibrium is balanced between gravity pull and pressure push. In a quiet valley before dawn, cold air gathers at the lowest ground. Air above adds weight, and the lowest layer becomes denser. The valley needs no lid to create the layering. Weight and pressure alone create a calm stack. In the star, the same logic fills a sphere rather than a hollow. Gravity pulls inward everywhere. Pressure pushes outward everywhere. When gravity tightens a layer, the layer warms. Warming increases particle motion and raises pressure. Raised pressure pushes back and slows the tightening. When pressure loosens a layer, the layer cools. Cooling lowers pressure and lets gravity regain control. This feedback keeps the shape steady without any fixed scaffolding. The pressure gradient is the map of that support. Pressure is higher below because more weight sits above. The rule remains true without any flaw. Each small volume presses on the volume beneath it. The chain continues down to the core. Support is shared through countless collisions. Particles collide and trade momentum in all directions. No single collision matters. The combined effect becomes a smooth pressure field. That field changes with radius like a gentle slope. It never becomes a cliff. One simple point becomes clear. The star is held up by gradients, not by strength of material. A second slow scene forms deeper down. A small parcel of gas drifts along an invisible level where pressure matches its surroundings. It does not fall quickly. It does not rise quickly. It spreads sideways into a faint sheet. The sheet curves through the interior like a contour line made of mist. Nearby, another sheet sits at a slightly different depth. The spacing between sheets shrinks toward the center. The view suggests a three-dimensional landscape made only of pressure. Another point becomes clear. Where the gradient is steep, a small shift in depth changes conditions a lot. Where the gradient is gentle, large motions are needed to change conditions much. A gentle scale shift now unfolds from moments to ages. Collisions happen in instants. Pressure adjusts quickly when temperature changes. The overall structure changes far more slowly. The stable phase lasts about 10 billion years, like many cycles of mountain ranges rising and wearing down on a rocky world. This long span is possible because disturbances are smoothed out. If a layer compresses slightly, pressure rises at once. The rise pushes outward and limits further compression. If a layer expands slightly, pressure falls at once. The fall lets gravity pull back and limits further expansion. This is the quiet springiness of a gas star. It resists large swings by correcting small ones early. Pressure waves are gentle compressions that travel through gas. A passing wave slightly increases density in one region. It then lets density relax as the wave moves on. Like a soft ripple moving through tall reeds, the effect is real but brief. Like a faint shiver crossing a cloud bank, the motion is felt as rhythm rather than as force. Why it matters becomes simple. Waves sample different depths as they travel. Their travel times depend on local density and pressure. When a wave reaches the outer layers, the surface texture shifts by a tiny amount. Bright cells and dark lanes become a little sharper, then a little softer. Broad bands of slightly altered brightness drift across the disk. They fade before any strong pattern can form. Another detail becomes clear. The star can carry internal messages without changing its steady glow. A limit of observation sits at the center of this picture. The interior pressure field cannot be seen directly through the star. Escaping light comes from the outermost layers only. Scattering erases detailed information from deep regions long before light leaves. Even wave traces are blended at the surface. Many different deep patterns can produce similar surface rhythms. The limit is one of resolution and indirect inference. A signal would reveal averages. It would not reveal a sharp map of pressure at depth. Yet the constraint is still powerful. Overall size and total mass restrict the allowable pressure gradient. A more compact star needs a steeper rise of pressure with depth. A more extended star needs a gentler rise. Steady fusion also requires a compatible temperature profile in the core. Temperature controls fusion rate. Fusion controls heat supply. Heat supply supports pressure. Pressure supports the whole layered stack. A steady consequence follows from these links. The star cannot drift far from balance without changing its brightness and size together. A final interior scene slows near the center. The deepest region is brighter and denser. Pressure contours crowd together there. Small radial steps change conditions strongly. The core is not a boundary. It is a region where the gradient is steepest and the feedback is most sensitive. Over long time, hydrogen in the core is converted into helium. Helium changes how pressure responds to temperature in the deep region. The core must contract slightly to stay hot enough for fusion. Contraction steepens the inner gradient. The change is gradual and quiet. It sets the stage for a structural rearrangement rather than a sudden flare. In the next passage, core hydrogen thins enough that burning shifts into a surrounding shell. How can a star begin to transform while its light still feels steady? The transformation starts when hydrogen in the core becomes scarce, and fusion shifts into a thin surrounding shell. In the center, helium accumulates as an ash of the earlier phase. That helium-rich region still holds heat, yet it produces less new energy. Gravity then pulls a little harder than before. The central region contracts. Density rises inward in a steeper gradient. Temperature rises with the compression. Pressure rises as particle motion becomes more vigorous. The core does not change in a rush. It tightens by small steps over long time. Each step warms the layers just above the center. A new burning zone appears just outside the shrinking core. The contracting center presses on the layers above it. Those layers are still rich in hydrogen. They heat until hydrogen fusion begins there instead. Shell burning is fusion in a narrow layer around a core. The old center grows quieter while a thin belt around it becomes active. It resembles a coral reef brightening at the rim around a still lagoon. This matters because the star can brighten as the very center becomes less productive. The belt is thin in radius. It sits where temperature crosses the threshold across a short depth range. Below it, the gas is hydrogen poor and cannot sustain the same reaction. Above it, the gas is cooler and less reactive. The burning layer therefore stays confined like a narrow seam. The sensitivity of that seam shapes the whole transition. A thin seam is sensitive, so small changes in compression can change the power output. The surface can respond later and more gently. At this distance, an interior cutaway looks like a dim central sphere wrapped by a bright seam. The seam is slender compared with the star's full radius. It glows as a narrow luminous ring embedded inside translucent shells. Below the ring, the helium-rich center is denser and more uniform. Above the ring, the envelope is broader than before. It is less dense on average, yet it reaches farther outward. Layers still grade smoothly from one to the next. Over long time, the seam drifts outward through the star's mass. The helium-rich center grows as the shell leaves more ash behind. The bright seam does not sit at a single fixed depth. Its position shifts slowly as hydrogen is consumed in that belt. Yet it remains thin because the threshold is crossed over a short range. Energy from the shell pushes outward through the overlying gas. Scattering and slow mixing smooth the flow into a steady outward leak. The surface does not flare in response to each inner change. The envelope responds by expanding. It expands until pressure and gravity match again in the stretched outer layers. Expansion does not add new matter. It changes the spacing between layers. Pressure still rises inward. The same mass is spread across a larger volume. The outer layers cool because expansion lowers density and reduces collisions. The visible surface shifts to a cooler color. The disk can look redder even while total brightness increases, because a larger surface can radiate more light overall. The change feels paradoxical at first. Cooler surface and greater total output can coexist. A larger area can outweigh the cooler glow per patch. Surface detail shifts as the outer layers stretch. Bright patches can appear larger in scale. Dark lanes between them can broaden and soften. The rim can look slightly dimmer than the center. Slanted paths near the edge skim cooler layers. The visible boundary where light escapes stays thin and it keeps a crisp edge. A slow visual scene forms around the star. The outer glow puffs outward into a broad halo. Brightness fades with radius in a smooth gradient. The expanded layers look like stacked veils. Each veil is more transparent than the one beneath, yet each veil spreads the same light over more space. The star seems larger in the dark around it. The colour deepens without drama. Time stretches across this stage. The move from core burning to shell burning takes about 100 million years. That span is like 100 million ocean swells passing a reef line in unhurried sequence. Within that long interval, small motions still happen quickly. Rising flow and sinking flow can overturn in hours. Local patterns shift and dissolve while the global structure drifts. Short rhythms and long rhythms coexist in one object. This gentle scale shift makes the change feel calm, even while the interior keeps evolving. The inner core continues to contract as helium accumulates. The shell continues to supply energy. It can strengthen as the core grows denser beneath it. Shell output depends strongly on temperature. A slight contraction can raise the shell temperature and increase fusion. The envelope responds by expanding and cooling. Expansion then lowers pressure near the shell and can soften the increase. The feedback keeps the evolution smooth. It also means the star can drift through a sequence of sizes rather than snapping to a new state. The drift is slow and the direction is steady. A limit of observation becomes unavoidable here. The bright shell cannot be separated from the surface, glow by light alone. Scattering in the envelope removes precise depth information from outgoing radiation. Many different shell thicknesses can yield similar surface color and similar total brightness. Even perfect knowledge of the disk's brightness would still blend contributions from multiple layers. A signal would carry an average, not a slice by depth. The interior must be inferred from surface behavior and from the requirement that gravity and pressure balance at each layer. This limit is not a lack of attention. It is a limit set by how light loses memory of where it begins. The stage sets the direction for the next transformation. Core contraction continues. Shell output grows gradually. The envelope becomes larger and cooler at the surface. The star steps away from its long, steady phase and toward a true giant form. The next passage follows this swelling in greater depth as the outer layers expand into a red giant and the inner core tightens further. What makes a red giant feel like the same star in a larger disguise? The star expands because shell burning adds energy to the outer layers faster than they can stay compact. The core is now mostly helium. It contracts and warms without producing much new power. Just outside, a thin hydrogen-burning shell provides the main energy supply. That energy pushes outward through the envelope. The envelope responds by swelling. Density drops in the outer layers. Temperature at the visible surface drops as well. A cooler surface can still sit on a brighter star if the radius grows enough. At this distance, the disk becomes larger and softer at the edge. Limb darkening deepens because shallow lines of sight sample cooler layers. The photosphere remains a thin boundary where light escapes. Its thinness creates a clear edge even for a larger star. The change is a reshaping of gradients, not a rebuilding of matter. A slow scene begins close to the surface. Broad bright patches drift across a reddish glow. Dark lanes between them look wider than before. The bright patches are convection cells that have grown in scale. The outer convection zone deepens as the envelope expands and cools. Warm gas rises and cool gas sinks in larger, slower rolls. Motion remains present without sharp turbulence. The surface seems to breathe in slow patterns. The red colour is not a stain. It is a shift in the balance of wavelengths, leaving the photosphere. Cooler surfaces radiate more of their light toward the red and infrared. Another payoff settles in quietly. The star becomes red not because it cools everywhere. It becomes red because the expanded skin is cooler, while the interior remains extremely hot. The core can be hotter than before even as the surface cools. This is a gentle scale shift between inside and outside. Deep layers tighten and heat. Outer layers loosen and cool. The two changes happen together because gravity and pressure must stay balanced. A deeper interior view shows the structure like a small dense center wrapped by a luminous seam. Above the seam layers spread outward into a huge envelope. The seam is the hydrogen shell. It is thin and bright because conditions cross the fusion threshold over a short depth range. Its energy production is very sensitive to temperature. A slight contraction of the helium core can raise shell temperature. Shell output can increase. The envelope then expands a bit more. Expansion cools the surface further. This feedback makes the star drift outward in size. It does not jump suddenly. The drift is slow because energy transport and structural adjustment take time. A visual anchor forms around the star in its extended phase. The outermost layers are so thin that they become translucent. A faint halo surrounds the disk. The halo has a smooth brightness gradient that fades into dark space. Within the halo, irregular arcs and wisps appear where density is slightly higher. These wisps are not separate clouds. They are parts of the star's own envelope where convection and pulsation create gentle density contrasts. The envelope has no solid ceiling. It is a gas that becomes thinner with radius. The transition from star to surrounding space is gradual. Another payoff becomes clear. A red giant is not a new object layered on top of the old star. It is the same mass redistributed. A large fraction of the mass still sits in the compact core region. Most of the volume sits in the tenuous envelope. This difference between mass and volume is one of the quiet surprises of the giant phase. It is like a loaf of bread rising in an oven. The same flour becomes a larger shape filled with airy pockets. The crust becomes wide and thin. The inside becomes mostly space between bubbles. The loaf looks much larger, while most material remains concentrated in denser regions. The analogy captures a key point without needing harsh numbers. Expansion creates volume more than mass. Another scale shift unfolds from hours to eons. Surface patterns can change in days. The overall radius changes over millions of years. The energy driving the swelling comes from slow core contraction and steady shell burning. The steady glow can hide an internal change that keeps accumulating. Helium ash grows in the core becomes denser. Degeneracy begins to matter. Degeneracy is pressure from packed electrons resisting further compression. It behaves differently from ordinary thermal pressure. It does not depend strongly on temperature. This matters because it changes how the core responds to heating. In a normal gas, heating causes expansion and cooling. In a degenerate core, heating may not cause immediate expansion. The core can store heat without expanding much. That sets the stage for a rapid ignition later. Another interior scene slows near the center. Pressure contours crowd together. Density rises steeply inward. The helium core has a sharper gradient than before. Above it, the hydrogen shell forms a bright narrow band. The band is like a thin glowing bracelet around a dark bead. Outside, the envelope is vast and diluted. Each layer is a gentle veil. Convection mixes these veils. Mixing can dredge up material processed deeper down. The surface composition can shift gradually as deep layers are stirred. The shifts are subtle. They change how the photosphere absorbs and emits certain colors, yet the overall red glow remains dominant because surface temperature is low. A limit of observation rests inside this giant structure. The helium core is buried under an enormous envelope. Escaping light comes from the photosphere and a shallow region beneath it. Scattering and absorption erase the detailed signature of the core. The core's degeneracy and exact temperature profile are inferred indirectly from global properties like size and brightness. Several internal arrangements can match the same surface output within uncertainty. The limit is one of indirect inference and blended signals. The core remains a hidden engine room whose details cannot be read directly, yet the trend is steady. The helium core keeps contracting. Temperature in the core rises. Degeneracy pressure supports the core without needing high temperature. Eventually conditions cross the threshold for helium fusion. In the next passage, ignition arrives beneath a calm surface. The core changes quickly while the exterior remains soft and red. How can an interior switch on abruptly while the surface keeps a slow red glow? Helium ignition begins rapidly in the compact core, while the outer layers remain buffered by long transport times. The core is now rich in helium, and supported partly by degeneracy. Degeneracy is pressure from packed electrons resisting compression. It does not relax much when temperature rises. That single feature changes the character of the moment. In an ordinary gas, heating causes expansion and cooling. In a degenerate core, heating can build without immediate expansion. The core contracts over long time. It grows denser. Temperature rises as gravity squeezes. The hydrogen shell above continues to burn and add ash. The ash increases the core mass. Each addition increases the squeeze. At some point, helium nuclei begin to fuse. Helium fusion is helium nuclei join and form carbon-releasing energy. The onset is not gentle. It is sensitive to temperature. A small rise in temperature increases the reaction rate strongly. That increased rate releases more heat. More heat raises temperature further. The feedback accelerates. The core does not expand quickly enough at first to calm it. The ignition is called a helium flash, yet it does not produce a surface flare. Energy is spent internally to change the core state. It goes into lifting degeneracy and expanding the core region. A calm payoff settles in early. The outward appearance stays quiet because the internal release is absorbed by structural change rather than sent straight outward. A visual anchor forms in the deep interior. A bright zone blossoms within the helium core like a soft lantern turning on behind thick fog. The glow is not a point. It is a region that spreads through the central volume. Pressure contours that once sat tightly packed begin to loosen. The density gradient in the core becomes less steep as expansion begins. The expansion is not large in radius compared with the whole star. It is large in effect. It changes how the core supports itself. Once degeneracy is reduced, thermal pressure matters again. The core can respond to heating by expanding. That response slows the runaway. The flash therefore peaks and then subsides. The core settles into a new balance where helium burning can proceed more steadily. Another payoff becomes clear. A rapid ignition can lead to a stable stage because the same physics that caused the runaway also provides its braking once degeneracy lifts. The energy release is enormous in the deep interior, yet it is trapped by layers above. Light behaves as scattered drift in dense gas. It cannot carry a sharp impulse outward. Heat first spreads through the core. It then works upwards slowly. The outer envelope remains extended and cool. The photosphere continues to radiate gently in red. The convection pattern near the surface changes only slowly. It does not know about the core event in any immediate way. Time creates a strong scale shift here. The flash itself can unfold in a short span compared with the star's life. The surface responds over much longer intervals because energy transport is slow. The contrast resembles a stone dropped into deep mud. The impact is sharp at the point of contact. The surface of the mud moves only as a broad, slow swell. This analogy keeps the moment calm. It also points to a physical reason. Dense layers, damp, quick signals. Another scene forms between core and surface. The hydrogen shell continues to burn during and after the flash. Its position may shift as the core expands. The shell can cool slightly because the core beneath it is less compressed. Cooling reduces shell output for a time. The envelope can contract modestly. The star can become smaller and less luminous than at the tip of its red giant rise. The surface temperature can increase a little as the radius shrinks. Color can shift away from the deepest red. The change is not dramatic. It is a quiet reconfiguration. The star moves on to a more stable helium burning phase. Helium burning now happens in the core. Hydrogen burning continues in a shell above it. The structure becomes layered again, yet with a new fuel at the center. A physical detail becomes prominent in this stage. The core is compact and dense. The surrounding shells are thinner in density. The gradient at the boundary between core and shell is steep. Heat flow across that boundary shapes the star's new size. Another payoff settles in. The star's giant envelope was driven by shell burning around an inert core. Once the core itself burns helium, the need for an extremely strong hydrogen shell can ease. The envelope no longer needs to be as bloated to carry the energy flow. That is why the star can shrink from its maximum red giant size after helium ignition. A limit of observation remains central. The helium flash cannot be seen directly. Escaping light is formed far above the core. Scattering and absorption erase the detailed timing and shape of the ignition. A signal would show only the star's gradual changes in brightness and colour. It would not reveal the internal peak power or the exact pattern of burning inside the core. Models infer the flash from the need to lift degeneracy and from population trends among similar stars. The limit is one of indirect inference and layered opacity. Fine details remain uncertain because the core is hidden behind thick gas, yet the qualitative sequence is firm. A degenerate helium core contracts. Temperature rises, helium ignites rapidly. Energy lifts degeneracy and expands the core. The runaway ends and steadier helium burning begins. A final visual anchor returns to the surface. The red disk appears slightly tighter. The limb darkening softens a little as the outer layers become less extreme. Convection cells still drift across the photosphere. Their scale is still large compared with the main sequence. Their motion remains slow. The star's light feels calmer again after the peak of its giant expansion. The next passage follows the steadier phase that comes after the flash. It traces how helium burning builds carbon and oxygen, and how shells continue to shape the outer layers. After the brief interior ignition, the star appears to settle into a different kind of calm. Helium now burns in the core and provides a steadier center. The swollen red envelope relaxes slightly. The disk becomes smaller than at its most expanded size. The color shifts toward a warmer yellowish tone. The change is gentle and slow. It reflects a new balance between core power and envelope structure. Inside the core is no longer locked by strong degeneracy. Thermal pressure matters again. Heat can now cause expansion. Expansion can cool the core and soften the reaction rate. This feedback prevents another runaway. A small payoff arrives early. The same physics that once allowed a flash now supports a stable stage. The core becomes a controlled furnace rather than a sealed container. Helium fusion is helium nuclei join and release energy. In a sun-like star, 3 helium nuclei combine to form carbon. Triple alpha is 3 helium nuclei combine into carbon. In a cold shoreline pool, salt can remain dissolved until a threshold is crossed. Then crystals begin, and growth accelerates in place. The core behaves in a similar threshold way, yet it is held in check by expansion. Carbon begins as a product of helium joining. Some carbon then joins with helium to form oxygen. The details depend on temperature and density. The result is a growing mixture of carbon and oxygen in the core. This mixture is not layered into hard shells. It is blended by motion within the burning region. A slow interior scene forms. The core is a bright oval volume with a smoother glow than the shell above. Within it, broad overturning flows circulate. Warm material rises from deeper zones. Cooler material sinks along curved sheets. The motion is driven by heat release in the center. It mixes fresh helium into hotter regions. It carries newly made carbon away from the hottest spots. It also keeps the core composition fairly uniform. Another payoff settles in. Mixing spreads fuel so the core burns more evenly. Even burning makes the star more stable. Above the core, the hydrogen shell remains active. It sits as a thin belt where temperature crosses the threshold for hydrogen fusion. The belt still produces helium ash. That ash settles onto the core and slowly increases its mass. The star therefore has 2 energy sources at once. Core helium burning provides a baseline. Shell hydrogen burning adds an outer contribution. The envelope responds to the combined flow. Its layers adjust their spacing until gravity and pressure match again. The star does not need to stay as bloated as before. A core that produces its own power can reduce the extreme temperature gradient that once forced a huge envelope. The envelope contracts slightly. Surface temperature rises slightly. Light leaving the photosphere shifts towards shorter wavelengths. The surface remains textured by convection. The texture is calmer and smaller in scale than at the peak red giant size. The rim still shows limb darkening as a smooth brightness gradient. Another payoff appears. A star can shrink while remaining luminous because the interior power is redistributed, not removed. The boundary between core and shell becomes a key physical detail. Density changes quickly across that boundary. Temperature also changes quickly. The gradient is steep because the core is compact. The shell is thin and hot. The layers above the shell are far less dense. The steep gradient shapes how waves and flows move through the interior. It also shapes how fresh material is supplied to burning zones. A second visual anchor appears inside the star. The bright core is enclosed by a thin, glowing ring of shell burning. Outside the ring, the envelope looks like faint layers of mist. Each layer is slightly cooler than the one beneath. Opacity changes with depth, so the path of light changes with depth. In deeper layers, light scatters often and drifts outward slowly. In outer layers, convection can carry heat more directly. The boundary between these transport regimes shifts with the star's radius. As the star contracts from its giant peak, that boundary moves. Convection becomes less dominant at some depths and more dominant at others. This rearrangement helps set the star's new surface temperature. Another payoff arrives. Surface color is a structural decision made by the whole interior, not a surface stain. Time stretches again into a calm scale shift. Core helium burning lasts about 100 million years, like a long era, in which a coastline can change shape many times under steady tides. Within that era, convection cells turn over in days. The shell burning rate changes slowly over thousands of years. The envelope radius drifts over millions of years. Short rhythms sit inside long drifts without conflict. The star can look steady in any single moment, yet its internal ledger keeps changing. Helium in the core is steadily converted into carbon and oxygen. The core therefore grows heavier in mean particle mass. That changes how pressure responds to temperature. It also changes how dense the core must be to maintain the same pressure. As helium is depleted, the core slowly contracts again to keep burning. Contraction raises temperature. Raised temperature increases reaction rate. Increased reaction rate raises heat output. Expansion then responds and cools the core. The feedback remains, yet the baseline conditions drift as composition changes. Another payoff settles in. Stability does not mean sameness. It means slow correction around a moving target. A limit of observation sits quietly inside this stage. The core is hidden behind layers that scatter and absorb outgoing light. No direct image can show the convective flow patterns in the burning core. The boundary of the convective region is not a visible surface. Its location must be inferred from global properties. Even those properties can match multiple internal models within uncertainty. A signal would blend contributions from many depths. It would carry averages rather than fine structure. This is a limit of resolution and indirect inference created by opacity and scattering. The star's surface shows the end result, not the detailed path. Yet the broad consequences remain clear. Helium burning builds carbon and oxygen. The hydrogen shell continues to add helium ash. The envelope stays far more extended than in the original main sequence phase. The star now sits in a quieter middle ground between its earlier red giant peak and its future late instability. The core is steadily transforming into a compact carbon-oxygen remnant. That remnant will later support shell burning above it in a more extreme way. The next passage follows the gradual shift as core helium becomes scarce. It traces how shell burning strengthens again, and how layered shells begin to dominate the star's future changes. Why does the late giant phase feel like a slow heartbeat rather than a steady glow? The heartbeat comes from thermal pulses in a thin helium burning shell beneath a broad envelope. Core helium burning has now declined. The center has become a compact carbon-oxygen core. It does not fuse carbon in a sun-like star. It contracts and cools slowly while remaining very dense. Above it, two shells can operate. A helium shell lies closer to the core. A hydrogen shell lies farther out, The hydrogen shell burns steadily most of the time and leaves helium ash beneath it. That ash piles onto the helium shell. The helium shell then grows thicker and more compressed. When it reaches a critical state, helium burning ignites strongly in that shell. The ignition is brief compared with the quiet intervals. It releases a surge of heat. That heat pushes on the layers above. The envelope expands. Expansion cools the shells. The helium shell then weakens again. The star returns to a quieter interval. This repeating cycle is a thermal pulse. Thermal pulse is brief shell ignition followed by expansion and cooling. A calm payoff arrives early. The pulses do not come from surface storms. They come from a deep timing mechanism set by ash piling up and then releasing. A visual anchor forms inside the star. A compact dark core sits at the center. Around it is a bright thin ring where helium shell burning flares. Above that ring a broader zone glows more gently where hydrogen shell burning continues. Beyond that the envelope becomes a vast translucent sphere. Its density falls outward in a smooth gradient. In the envelope convection rolls become huge and slow. They mix material through thick layers. During a pulse, the bright helium ring thickens and brightens for a short time. It looks like a faint ember band turning up briefly within fog. The band then fades as the envelope swells and cools. Another payoff settles in. The pulse energy is spent mostly on rearranging the star's structure. It lifts layers outward rather than blasting light into space at once. The surface responds with a slow brightening and dimming. The response is softened by transport time and by the enormous heat capacity of the envelope. The surface therefore shows a gentle rhythm. The rhythm is not perfectly regular. Each pulse changes the conditions for the next. A slow scene forms at the surface. The disk looks red and very large again. Limb darkening deepens toward the rim. Broad bright cells drift slowly. Dark lanes curve like wide trenches. During a pulse the overall glow increases. The outermost layers expand. The surface temperature can drop slightly even as total brightness rises because the area increases. After the pulse, the envelope contracts modestly. The colour can shift a little. The shifts are subtle. They resemble a breathing fabric that stretches and relaxes, never snapping taut. The fabric image matters. The envelope behaves like a thick cloth held under tension by gravity. Heat from below loosens the weave and lets it billow. Cooling tightens it again. The cloth is not a material sheet. It is a changing density profile in gas. Yet the feel of a slow billow captures the response. A gentle scale shift appears between deep timing and surface motion. The helium shell ignition can rise and fall in years. The surface radius can drift over centuries or longer. The core composition changes over tens of thousands of years. The whole star evolves over millions of years. Many clocks overlap. The pulses provide the most noticeable rhythm within the late stage. Another payoff becomes clear. The pulses also drive mixing that changes what the surface is made of. Convection already stirs the envelope. During and after a pulse, the boundary between convective regions can move. Deep material can be carried upward in an episode called dredge up. Dredge up is deep material mixed upward into the envelope. It can bring carbon-rich material closer to the surface. The surface then has slightly different opacity. Opacity alters how radiation escapes. That can influence the star's colour and the ease with which the envelope loses mass. Another physical detail becomes prominent in this stage. The star develops extended outer layers where gravity is weak and density is low. In those layers, small pushes from radiation and from pulsation can lift gas outward. The lifted gas can cool and form dust grains. Dust can absorb and scatter light strongly. When dust forms, it can be pushed outward more easily by the star's radiation. This creates a slow wind that carries material away. The wind is not a jet. It is a broad outflow from a large fraction of the surface. The outflow can become denser after a pulse because the envelope is more extended. A visual anchor appears outside the star. A faint expanding veil surrounds the red disk. The veil is not smooth. It has nested arcs like ripples frozen into mist. Each arc marks a past episode of stronger outflow. The arcs spread outward and thin as they move. Light passing through the veil is softened. It is reddened slightly by scattering. The star begins to hide itself within its own departing material. Another payoff settles in. The late pulses are not only internal events, they help strip the envelope away and prepare the core to be exposed. A limit of observation rests inside this picture. The shells are thin and deep. Their exact thickness and temperature profile cannot be seen directly. Escaping light forms in outer layers and carries only blended clues. Dust in the wind can further obscure the inner regions. Even the pulse cycle length can vary and can be masked by the changing envelope. A signal would reveal surface brightness changes and spectral shifts. It would not reveal the detailed structure of the helium shell flash itself. Models infer the shell behavior from population patterns and from the need to explain mass loss and composition changes. The limit is one of indirect inference and layered opacity, yet the mechanism remains coherent. Helium ash accumulates. Helium shell ignites briefly. The envelope expands and cools. Convection and dredge-up reshape composition. Outflows strengthen and carry mass away. Each loop makes the envelope lighter. Each loop leaves the core more dominant. The next passage follows what happens when the envelope becomes thin enough to be lifted away more decisively. It traces how the departing gas becomes a glowing planetary nebula around a newly revealed hot remnant. What remains when a swollen giant loses its grip on its own outer layers? A planetary nebula forms when the envelope drifts away and is lit by ultraviolet from the hot remnant. The change begins quietly in the extended outer atmosphere. Gravity is weak there because the radius is large. Density is low and the gas is cool enough for dust grains to form. Dust does not shine by itself. Dust changes how light moves through the gas. It absorbs and scatters starlight and turns part of it into heat. When the envelope is lifted by pulsation, and radiation dust can be carried outward with the flow. The flow is broad and slow at first. It thickens in some regions and thins in others. The result is not a smooth sphere of gas. It is a layered outflow with ripples in density. At this distance, the fading red giant looks like a large dim disk inside a pale haze. The haze is uneven. It shows faint arcs and patches where the outflow is denser. A small payoff settles in early. The nebula is not created by a sudden explosion. It is assembled by many gentle episodes of loss that finally detach the envelope. As mass leaves the remaining core becomes easier to see in principle, yet it is still wrapped in gas. The core is compact and hot. Its surface temperature rises as the envelope thins. The spectrum shifts toward ultraviolet. Ultraviolet does not travel far in dense neutral gas. It is absorbed close to the source at first. That absorption changes the gas itself. Ionization is atoms lose electrons after absorbing energetic light. When atoms are ionized, they can later recombine and emit light at specific colors. The glow of a planetary nebula comes from this cycle. It is not reflected light like a dusty cloud. It is light produced within the gas as electrons return to atoms. Another payoff becomes clear. The nebula glows because the gas is changed by radiation, not because it is merely illuminated. A slow scene forms around the remnant. A bright central point sits where the star used to be. Around it, a thin shell begins to brighten at its inner edge. The bright edge is an ionization front. It is a moving boundary where ultraviolet has reached and changed the gas. The front is not a hard wall. It is a narrow region where the fraction of ionized atoms rises quickly with radius. Inside the front, gas is more ionized and warmer. Outside, the front gas is less ionized and cooler. The transition creates a distinct rim in brightness. The rim is sharper where density is higher. It is softer where density is lower. The shell is not perfectly round. It can be slightly elongated. It can be pinched in places by earlier density structure. A second payoff arrives. The shape of the glowing shell preserves the memory of how the envelope was lost even after the star itself has changed. Within the bright rim, small dark knots appear. Each knot is a dense clump that resists ionization for longer. The clump casts a long, teardrop-shaped shadow of neutral gas away from the center. The shadow is not a true darkness. It is a region where ionization lags behind. The shadow tapers because the surrounding ionized gas expands around it. The shell therefore becomes a lacework of bright filaments and dim tails. At this distance, the structure resembles a thin, translucent fruit skin pulled taut and then wrinkled at the edges. The edge is scalloped. Brightness gathers along the scallops, where density is slightly higher. Between scallops, the shell looks thinner and more transparent. Another payoff settles in. Small clumps can control the apparent texture, because emission depends strongly on density. A slight increase in density can make a filament much brighter. The shell continues to expand. Its speed is about 20 kilometers per second, enough to cross Earth in about 10 minutes. The number feels large and gentle at the same time. The expansion is steady but not fast compared with many cosmic motions. It is fast compared with winds on any rocky world. This scale shift matters because it links a delicate glow to a measurable outward drift. Over thousands of years, the shell can grow to a vast size. Over the same span, the remnant stays small. The core remains compact and hot while the shell moves outward into colder space. A signal would show the shell growing and fading at once. Growth spreads the same gas over a larger volume. Fading occurs because density drops as the shell expands. Lower density means fewer recombinations and less emitted light per unit volume. Another payoff becomes clear. A planetary nebula is brightest during a narrow window when the remnant is hot and the shell is still dense enough to shine. The glowing phase depends on timing. The remnant heats as it contracts toward a white dwarf state. The shell thins as it expands. If the remnant heats too slowly, the shell can disperse before strong ionization begins. If it heats quickly, the shell can be lit while it is still compact and bright. In many cases, the timing aligns well enough to produce a vivid nebula. The nebula then gradually fades as the shell becomes too diffuse. The rim loses contrast. Filaments break into faint threads. The teardrop shadows lengthen and then blur as density differences wash out. A slow, visual anchor holds this stage. A bright oval ring floats in darkness with a faint outer halo. Inside the ring, the central point is sharp and pale. Along the ring, knots appear as beads that interrupt the glow. Each bead has a soft tail that points away from the center. The tails are aligned like grass pressed by a steady current, yet the current is radiation and expansion. Another payoff settles in. The nebula's fine structure is a map of competing processes, density clumping against ionization smoothing. A limit of observation sits naturally in this glowing geometry. The shell is three-dimensional, yet any distant view collapses it into a two-dimensional silhouette. A bright ring can be a true ring, or it can be a hollow sphere seen in projection. An apparent knot can be a dense clump, or it can be a fold where two layers overlap along the line of sight. The thickness of the shell is difficult to measure directly, because brightness depends on density squared. A small region of high density can dominate the light. This makes mass estimates uncertain. It also makes the history of mass loss hard to reconstruct in detail. The limit is one of projection and indirect inference. The glow reveals where ionization and density combine, not the full distribution of matter. Even with these limits, the broader story remains stable. The envelope is removed by long late-stage outflow. Ultraviolet from the exposed remnant ionizes the departing gas. Recombination produces the visible glow. Expansion lowers density and fades the light over time. The nebula therefore marks a brief boundary between a giant star and a compact remnant. The central object grows hotter for a time as it contracts. Then it begins a long cooling journey. In the next passage, the remnant is described as a white dwarf, small in size and supported by a different kind of pressure. What kind of star remains after the glowing shell thins into darkness? A white dwarf remains supported by electron degeneracy pressure while it slowly cools. The planetary nebula continues to expand and fade. Its filaments soften into a faint haze. The bright rim loses contrast as density drops. The central remnant stays compact and intensely hot. It shines as a pale point inside a much larger, dimmer envelope. Over time, the envelope becomes too thin to glow. The scene simplifies. Only the remnant remains as a small, hard light in empty space. A quiet understanding settles early. The star does not end as a cold stone. It ends as a dense object with stored heat and a different kind of support. Electron degeneracy is pressure from crowded electrons resisting compression. It comes from quantum rules rather than temperature. As the core contracts after envelope loss density rises until degeneracy becomes dominant. Once degeneracy takes over, further compression becomes difficult. The remnant finds a stable size without needing fusion. That size is about 7,000 kilometers across, similar to Earth. The number feels small beside a giant star. It feels large beside a rocky mountain range. This scale shift is one of the gentlest surprises in stellar evolution. A sphere that once filled a vast volume now becomes planet-sized while keeping much of its mass. At this distance, the white dwarf appears like a tiny bright bead. Its edge is sharp. Its limb darkening is subtle because the atmosphere is extremely thin. The atmosphere is only a skin compared with the dense interior beneath it. The skin is a gradient, not a shell. Pressure rises very quickly with depth in that skin. A small descent brings a large change in density. A signal would leave from only the outermost layers because deeper photons scatter and lose their path. Another understanding unlocks. The visible light is a surface symptom. The structure is set by the interior where electrons are packed close together. A slow internal view forms in imagination. The interior looks like a smooth globe with no convection cells and no bright seams. Temperature is highest inside and lower near the surface. The gradient is steady and steep. Heat flows outward by slow conduction through dense matter. Radiation no longer carries energy through a thick envelope. Convection no longer overturns large regions. The remnant is compact enough that gravity keeps layers tightly stratified. The surface gravity is strong, so heavier elements tend to sink below lighter ones. The atmosphere can become dominated by the lightest elements present. This chemical sorting affects how the surface radiates. A small payoff arrives. The white dwarf's colour and brightness depend on a thin skin, even though most mass is deep inside. The core is mostly carbon and oxygen for a sun-like star. Those nuclei sit in a dense sea of electrons. The electrons provide most of the pressure support. The ions contribute most of the heat capacity. This separation matters. Pressure remains high even as the object cools because degeneracy does not vanish with temperature. The white dwarf therefore cools without expanding much. Its radius changes only slightly. Its brightness falls as stored heat leaks away. The cooling is slow because the interior holds an enormous reservoir of thermal energy. It is also slow because heat must thread through dense material. A gentle scale shift follows from microscopic to cosmic. Electrons occupy quantum states and resist being squeezed together. That quantum resistance sets the size. The same object then spends billions of years radiating away its heat. The glow fades through a long sequence of temperatures. The spectral peak shifts from ultraviolet toward visible and then toward infrared. The object becomes dim and redder over immense time. Another visual anchor appears. The white dwarf sits alone after the nebula disperses. Around it, space is dark and sparse. The object looks like a white spark with a faint bluish halo close to the limb. The halo is not a separate cloud. It is a slight scattering effect in the thin atmosphere. The limb is crisp because the emitting layer is shallow. The disk is tiny compared with any earlier phase, yet it is still a sphere. Its shape is held by degeneracy against gravity. Another payoff settles in. The remnant stays stable because cooling does not remove its main support. Cooling changes luminosity, not the underlying pressure balance. As the white dwarf cools further, a new interior change can occur. Crystallization can begin in the core. Crystallization is ions arrange into a solid lattice as temperature drops. In dense matter, ions can settle into an ordered pattern. The process releases latent heat and can slow cooling for a time. It also changes how heat moves through the interior. A slow scene forms inside. A crystallized region begins at the center where density is highest. It grows outward as the object cools. The boundary between solid and liquid is not a sharp wall. It is a narrow region where ordering becomes favorable. The boundary moves slowly over long time. The interior becomes a quiet mixed state. A solid core sits beneath a still fluid mantle. Both are embedded in the same electron sea. Another payoff appears. Even after fusion ends, the remnant continues to evolve internally, yet in a gentle and silent way. A limit of observation becomes clear here. The interior cannot be seen directly. Only surface light escapes. Surface light is shaped by the atmosphere's composition and pressure. Pressure broadens spectral features and can smear out fine details. A thin atmosphere can hide a complex interior behind a simple spectrum. Cooling age estimates depend on models of the atmosphere and of crystallization. Small uncertainties in composition can shift the inferred age by large amounts. This is a limit of indirect inference rather than a lack of measurement. The object is too small and too distant for internal mapping by light alone. The interior story must be reconstructed from theory and from population trends. Another visual anchor returns to the boundary between object and space. The surface is smooth and uniform. There are no long-lived spots. There is no thick envelope to sculpt broad patterns. The surface emits steadily and quietly. The brightness decline is so slow that it appears constant over short intervals. The white dwarf becomes a long-duration ember in the cosmic night. It does not brighten again without an external source of matter. It simply cools. The cooling continues far beyond the era when the nebula was visible. The remnant gradually approaches the temperature of its surroundings. In the next passage, the long cooling path is followed across deep time. The focus shifts from a single object to the population of such remnants, and the quiet record they keep of ancient stars. A white dwarf looks steady, yet its light is a slow countdown. The remnant cools because no fusion replaces the heat that leaks away. The cooling is not a simple slide in brightness. It carries the memory of structure inside dense matter. The surface begins very hot and pale. It then drifts towards softer colours as heat escapes. At this distance, the object is a small disk with a clean rim. The disk is tiny against the star field. Its sharp edge comes from a thin atmosphere. The atmosphere is a shallow gradient where light finally escapes. Below that gradient, matter is so dense that photons scatter and wander. Heat moves outward in a slow and patient way. Another quiet understanding settles early. The white dwarf is supported by degeneracy, so cooling does not make it collapse. Cooling changes the glow, not the size. The remnant therefore becomes a stable storehouse of time. A slow scene forms around a group of old stars. A crowded swarm fills the view with many faint points. Some points are warm and reddish. Some are pale and dim. Between them dust is scarce and space is clean. Among the faint points, a thin chain of white dwarfs stands out by colour. Near the brighter end of the chain, the points are bluish-white. Farther down, they become cream-coloured and then dull red. The chain is not a line drawn on a chart. It is a physical pattern of fading lights in the same stellar family. Another payoff arrives. A cluster carries a built-in clock because its white dwarfs cool at predictable rates. Each remnant starts hot and then fades. The faintest visible ones mark the cluster's age. This is how cooling becomes a calendar. The calendar is not perfect. It is still a powerful guide. A white dwarf begins cooling when the envelope is lost. That start time depends on how long the star spent as a giant. In a cluster, many stars share a similar birth time. The cooling sequence, therefore, has a clear edge at the faint end. Past that edge, remnants are too faint or too cool to detect. The location of the edge becomes a time marker. The core composition matters. A carbon-oxygen core stores heat differently than a helium core. The atmosphere composition matters too. A thin hydrogen layer radiates differently than a helium layer. These details shift how quickly brightness declines. Another payoff settles in. Cooling is not only a loss of heat, it is also a change in how heat is released. A new interior process joins the story as the remnant cools. Crystallization is ions arrange into an ordered lattice. In dense matter, this ordering begins where density is highest. It begins near the center and slowly moves outward. This pattern is not intuitive at first. Many familiar freezing processes begin at a surface. Here the interior is the first region to become ordered. A natural analogy helps without adding noise. It resembles a young rocky planet whose metallic core solidifies first. The mantle can remain softer while the center becomes rigid. The analogy matches the direction of change. The center becomes structured before the outside does. Another payoff becomes clear. Crystallization releases latent heat and slows cooling for a time. The remnant can linger at certain brightness levels longer than expected. The effect is gentle but important for clocks. A slow interior scene forms. The central region becomes a quiet, solid sphere. Around it, a still fluid layer remains. The boundary between them is a thin zone. It is marked by a change in how ions move. The boundary is not visible from outside. It is a hidden shoreline inside dense matter. That shoreline moves outward over immense time. The outer atmosphere continues to radiate. The surface remains smooth. The disk keeps its crisp rim. The color continues its slow drift. The remnant becomes dimmer and redder. A broad-scale shift opens softly. The microphysics of electrons and ions sets the support and the heat flow. That microphysics then controls an evolution that lasts about 10 billion years, like the time needed for continents on a rocky world to drift and reshape ocean basins many times. The number is vast, yet it is still finite. It places the remnant in the long rhythm of a galaxy. In the cluster scene, bright stars may still shine. Dim stars may still burn hydrogen slowly. White dwarfs quietly fade among them. Their fading forms a second kind of history. Another payoff arrives. The faint end of the cooling chain can reveal whether the cluster is truly ancient or only moderately old. The method depends on detecting very faint light. It also depends on knowing distance and dust. Dust can redden and dim the points. Crowding can blend them together. Some remnants may have slightly different atmospheres. These variations can smear the edge, yet the overall shape remains informative. A limit of observation appears here, and it is specific. The faintest white dwarfs emit very little visible light. Their peak emission shifts into infrared. If the observing band misses that peak, the objects can appear to vanish early. Background confusion adds another limit. In a crowded field, a faint remnant can be lost among dim main sequence stars. Distance uncertainties add another limit. A small error in distance can mimic a large change in luminosity. Model uncertainties add a final limit. Cooling rates depend on crystallization and on the thickness of surface layers. This is a limit of inference from faint signals. It is not a lack of theory alone. It is a blend of weak light and model dependence. Another visual anchor steadies the mind. The cluster field is calm and dense. The brightest stars are sparse. The faint points are many and steady. The white dwarfs appear as tiny beads with subtle color differences. The brightest ones are cool white and sharp. The faintest ones are muted and hard to separate from the background. The chain of fading beads curves through the swarm like a gentle arc of cooling embers. The arc is not a trail of motion, it is a trail of time encoded in brightness. Another payoff settles in. Many white dwarfs together form a record of star formation history in a galaxy. If many formed long ago, there should be many faint ones. If many formed recently, there should be more bright ones. The distribution of brightness becomes a population fingerprint. Each remnant is a single point. Together they become a slow census. The census can hint at when stars were born and when they died. The census is softened by many effects. Different masses cool at different rates. Different atmospheres alter colors. Some remnants may have thin shells of helium, some may have traces of heavier elements that settle and reappear. Yet the broad pattern persists. Cooling is predictable in outline. Cooling is slow. Cooling is monotonic for isolated remnants. That monotonic fade makes a useful clock. As time stretches further, the remnant approaches a near-dark state. The term black dwarf is used for a white dwarf that has cooled so far it emits almost no light. In the current universe, such objects are expected to be extremely rare or absent because the required time is so long. The concept still has value as an endpoint. It clarifies that the remnant does not explode, it does not reignite by itself, it simply cools toward the background. Another payoff arrives. The end state is not dramatic. It is a gradual blending into the dark. The next passage widens the view beyond a single remnant. It follows what the cooling remnant means for the surrounding system and for the long, quiet future that follows. After the last bright shell fades, motion remains. Mass loss has already reshaped every orbit around the remnant. The change begins long before the nebula glows. It begins while the star swells into a giant and sheds material in a steady outflow. Each parcel of escaping gas carries away some gravity's grip. The remaining system responds without drama. Orbits expand because the central mass is lower. The expansion is gentle if mass is lost slowly compared with an orbital period. A small payoff settles in early. The planets do not need a push to move outward. The orbit widens because the center becomes lighter. The widening can be about 2 in radius, like a ripple ring on a pond growing to twice its size. The exact factor depends on how much mass is lost. The direction is consistent. Wider orbits become the quiet signature of the giant phase. At this distance, a surviving outer planet appears as a faint dark bead against the remnant's glare. The bead traces a slow path. The path is wider than before. The remnant sits at the center as a tiny white point. Between them, space is empty but not truly clean. A thin mist of dust can drift through the system. Some dust comes from the wind. Some dust comes from collisions in leftover debris. The debris can be stirred as gravity balances shift. Resonances move outward as the central mass declines. Small bodies can be nudged onto new paths. Some become more eccentric. Some become unstable. Another payoff arrives. The giant phase does not only move planets outward, it can also shake smaller bodies into fresh rearrangements. Closer in the story is harsher even without violence. The giant star's envelope can extend far beyond its earlier size. Inner orbits can be swallowed. Any object embedded in the outer atmosphere feels drag from gas. The orbit shrinks and circularizes. Heat rises in the engulfed region. Material can be stripped from the object. These details remain uncertain because the event is brief in the full lifetime. Yet the outcome is clear in outline. Inner systems are pruned. Outer systems migrate outward. A visual anchor forms from this contrast. Near the remnant, the region is sparse and dark. Farther out, a few distant worlds remain moving slowly in widened lanes. Between them, a faint belt of rubble can persist. The belt looks like a thin, smoky band seen edge on. It is not smooth. It has brighter patches where dust is denser. The patches drift and spread with time. Another payoff settles in. A system can look empty near the remnant and still hold a rich outer reservoir of small bodies. Over long time, some of that reservoir can leak inward. The remnant's gravity is strong close up. A minor body that passes too near can be torn apart by tidal forces. Tidal disruption is gravity pulling harder on one side than the other. If the object is weak, the differential pull can overcome its self-gravity. The result is not a single fragment. It becomes a stream of rubble. The stream wraps around the remnant and collides with itself. Collisions grind pieces into dust. Dust settles into a flat disk close to the remnant. The disk is warm compared with the surrounding dark. It can glow faintly at longer wavelengths. A slow scene appears. A thin, pale ring hugs the remnant like a whisper of smoke trapped in orbit. The ring has a sharper inner edge where material is hottest. It has a softer outer edge where dust is cooler and thinner. The surface brightness shows a gradient rather than a hard boundary. The ring is not a planet. It is a temporary structure made of ground down stone and metal. Another payoff becomes clear. The remnant can be fed by leftovers long after its nebula has dispersed. Some of that material falls onto the surface. The surface gravity is so strong that heavier elements sink quickly. The atmosphere is thin and stratified. If heavy elements are seen there, they cannot have remained since formation. They must have arrived recently. This becomes a tracer of accretion from debris. The idea is simple and calm. A clean atmosphere should become purified by settling. A polluted atmosphere implies ongoing supply. A signal would show lines from elements that should not persist in the upper layers. The lines are broadened by pressure in the dense atmosphere. The broadening can smear details, yet the presence itself can be a clue. Another payoff settles in. The remnant spectrum can reveal the chemistry of disrupted bodies without showing those bodies directly. The debris disk can also shape light in subtle ways. Dust can absorb and re-radiate. Dust can scatter and dim. If a thin cloud crosses the line of sight, the remnant can fade briefly. The fading can be uneven. It can have a soft onset and a slow recovery as dust clears. Such events can hint at clumps in the disk. The disk can also feed gas that forms a narrow emission region. That region can produce faint spectral features. All of these are indirect signs. They are quiet fingerprints rather than clear pictures. A limit of observation sits naturally here. The remnant is small and distant. The disk is thinner and fainter. Direct images rarely resolve the disk structure. Most information comes from changes in brightness and from spectra. Those measurements depend on distance and on dust along the path. They also depend on models of the atmosphere. Pressure broadening and gravitational settling complicate interpretation. A heavy element line can imply recent accretion, yet the accretion rate is difficult to pin down. The disk can be inferred from infrared excess, yet the exact geometry can remain ambiguous. A flat disk and a narrow ring can produce similar signals when unresolved. The limit is one of indirect inference and limited spatial resolution. Even with the limit, the main chain remains coherent. Mass loss widens orbits. Dynamical stirring can send small bodies inward. Tidal disruption makes debris. Debris can pollute the atmosphere. Another scale shift softens the view. A grain of dust only a fraction of a millimeter across can scatter light. That scattering can change the brightness of a star-sized remnant seen from far away. Meanwhile, the orbital evolution that delivers that grain can take millions of years. The smallest structures can create the quickest signals. The largest rearrangements unfold over deep time. This crossing of scales gives the late system its quiet complexity. Another visual anchor returns to the remnant and its surroundings. The white dwarf is a tiny, steady point. A thin disk lies close to it like a faint halo cut into a plane. Far beyond a surviving planet follows a widened path. The planet's shadowed face remains dark. Its motion is slow and regular. Between disk and planet, sparse dust drifts and thins. The entire system looks calmer than the giant phase, yet it is not static. It is a long after-image of earlier mass loss. The remnant's light continues to fade. The disk can thin as it is accreted or dispersed. The outer bodies continue their slow orbits. The next passage settles the whole arc into a final calm perspective. It follows the remnant's fading light and the quiet end of change. A star can fill a sky with light and still end as a quiet point. The life of a sun-like star ends with a white dwarf that cools and fades. The long arc is simple in outline. Fusion builds energy for most of the lifetime. Expansion and mass loss reshape the system near the end. The remaining core becomes compact and stable. At this distance, the final scene is spare and calm. A small pale disk sits in darkness. The disk has a crisp rim and a soft gradient across its face. The surrounding space is almost empty. Any earlier nebula has dispersed into a thin, invisible mist. The remnant's light is steady on short timescales. It is a slow ember on long timescales. Another understanding settles early. The end is not a sudden stop. It is a change of engine. Thermal pressure and fusion give way to degeneracy and stored heat. The remnant continues to exist as matter arranged into a dense equilibrium. The whole story can be held with only a few ideas. Fusion is the conversion of mass into energy in the core. Mass loss is the shedding of outer layers during the giant phase. Degeneracy is quantum pressure that supports the white dwarf. These ideas can feel abstract at first. They become calmer when tied to scenes. The main sequence is a stable glow from a compact core. The red giant phase is a swollen envelope with a bright extended surface. The Planetary Nebula phase is a shell of gas expanding and thinning. The white dwarf is a planet-sized remnant with a thin atmosphere. Each stage has its own texture and edge. Another payoff arrives. The visible form changes because the balance of pressure sources changes. During fusion, temperature and gas pressure matter most. After fusion, quantum rules and crowded electrons matter most. That shift is a quiet twist. It turns a vast star into a small, dense object. It also turns a bright lamp into a cooling ember. A single number can hold the timescale without strain. The remnant can spend about 10 billion years cooling like the time for a continent to drift across an ocean basin many times. The comparison keeps the scale gentle. It reminds that cooling is slow beyond ordinary intuition. It also hints at why the night sky can contain many white dwarfs at once. They last, they accumulate, they become part of the background of a galaxy. A new visual anchor carries the closing. The white dwarf sits near a faint ring of dust. The ring is thin and flat. Its inner edge is sharper where dust is warmer. Its outer edge is softer where density drops. The ring is a pale veil against darkness. Farther out, a surviving planet traces a wide orbit. Its motion is slow and silent. Its shadowed side remains dark. The orbit is wider than it once was because mass was lost. The system looks like a quiet pond after a storm has passed. Ripples are still present, yet the surface is mostly smooth. The analogy is not about water itself. It is about a system settling after a change in central weight. Another payoff settles in. Mass loss does not only create a nebula, it also relaxes the gravitational binding of the whole system. The outer architecture expands without needing a shove. A latent disturbance can still occur when small bodies drift inward. A small body can be torn by tides and become a dust ring. That ring can feed the remnant. The remnant's atmosphere can show traces of elements that sink quickly. Those traces imply ongoing supply. The same remnant can therefore tell two stories at once. One story is its own cooling. Another story is the late reshaping of leftover debris. The stories are read through light and through absence. They are quiet, but they are coherent. A limit of observation sits softly in the closing, and it is specific. The white dwarf is small and far. Its surface cannot be mapped in detail by direct imaging in most cases. Its interior cannot be seen at all. Cooling ages depend on models of atmosphere composition and crystallization. Disk geometry is inferred from unresolved light and from subtle brightness changes. Distance and foreground dust can mimic temperature shifts. Crowding can hide the faintest remnants in a field. These are limits of resolution and indirect inference. They do not erase the story. They simply blur some details at the edges. Another payoff arrives. Even with those limits, the major checkpoints remain readable, because they involve large changes in size and energy source. The main sequence lasts the longest and sets the baseline. The giant phase marks the turn toward expansion and mass loss. The Planetary Nebula is a short, luminous farewell from expelled gas. The white dwarf is the long remainder, dense and stable. Each checkpoint has a physical signature. Each signature connects to a pressure balance and an energy flow. This connection is the quiet backbone. It is why the narrative holds even when details are uncertain. A gentle scale shift returns the mind to the smallest and largest together. In the interior, electrons resist being crowded into the same states. That quantum rule produces pressure without heat. On the larger scale, a galaxy contains billions of such remnants. Over cosmic time, their faint light becomes part of the galactic glow. The fate of a single star is therefore not isolated. It is repeated many times across a galaxy. It becomes a common endpoint for stars of similar mass. The repetition makes the quiet ending feel less like disappearance. It feels like a transition into a vast population of cooled cores. Another visual anchor slows further. The white dwarf's limb stays crisp. The disk is small. The brightness is modest. The surrounding space has no bright filaments now. Only a faint dust ring remains. The ring shows a soft gradient. It is densest closer in. It thins outward. The planet's orbit is wide and empty. The system is stable and quiet. The remnant's light continues to drift downward in a slow curve that cannot be sensed moment to moment. The change is measured only over deep time. Another payoff settles in. The ending of a sun-like star is not a collapse into darkness. It is a long release of stored heat. It is a settling into quantum support. It is a gentle fading that keeps the remnant present for ages. The arc is complete. The early bright stability gives way to late expansion. The brief nebular glow gives way to long cooling. The final state does not demand attention. It simply remains. The next moments need no new mechanisms and no new mysteries. The same quiet physics continues. Light continues to travel outward. Heat continues to leak away. Space continues to open around the remnant. The scene holds steady and calm.